understand our universe forever. Black holes are one of the greatest in the universe. When you get close to a black hole, gravity starts behaving in strange ways. The flow of space-time towards the black hole becomes so strong, so fast, that no object, no information, not even light, can ever pass out of that boundary. Ultimately, we want to understand how the largest black holes in the universe feed and how they grow. This is a huge challenge. These black holes are very far away and basically invisible. However, anything falling towards the black hole will gain enormous amounts of energy that produces light. And this light shines bright enough for us to study this object, this newborn quasar, from the other end of the universe.
A quasar is the manifestation of a black hole. You know, in the movies quite often they say a black hole sucks everything in around it. That's not quite how it happens. We think that matter falls onto the black hole through an accretion disk. So stuff will fall towards a black hole, but it usually is coming in and misses by a bit, and so it goes into orbit around the black hole. And as it orbits around the black hole, the matter experiences friction. And it's that process of an accretion of matter that produces the quasar. The whole aim of these observations is to measure the size of the accretion disk in millimeters, as with a ruler, by colour. And in fact, that colour is reflecting temperature. And so we expect the size to increase as it goes out, and it's just how it increases that is really crucial.
The team of researchers working on our project are in locations scattered around the globe. We get together on conference calls every week or two to discuss observations and new results.
Okay guys, so where are we with these Hubble observations?
Well, we have a graph of observations of 1422.
How did it look?
The Hubble resolution is amazing, and the lens images are clearly separated.
Yeah, do you think the significant lens measure a temperature gradient?
So the difference in ratios is indicating a really clear microlensing signal, so it's looking pretty good.
Okay, so which quasar are we going to be analysing next?
Next up is 2026, discovered by our very own Dr. Webster. Really, it should be impossible to study these objects. It should be impossible to see right down to the accretion disk on the other side of the universe. But if you're curious enough and clever enough, then you can find a way.
We're looking at 7 or 8 very special quasars which are gravitationally lensed into multiple images, so we can actually see more than one image of the quasar. And so we can't pick those out, we have to just take them where we find them. It's a chance alignment. And the particular thing that we look for in gravitational lensing is a mass, such as a galaxy, between us and a luminous background object like a quasar. The light from the quasar bends around the galaxy, comes to our eyes. Our brain says it came in a straight line, and so we think that we've seen multiple images.
So that's the effect of the galaxy as a whole. But each of these paths of light is also affected by individual stars in that galaxy. And if those stars just happen to be lined up along one of those paths of light in just the right way, they cause different parts of that accretion disk to fluctuate in brightness. So as the quasar crosses that field of stars, the Hubble Space Telescope takes a series of photos. Each one uses a filter, so we block out all the unknown range of the colour of the light coming through. So we see different parts of the accretion disk magnified in different ways. By comparing these differences, we can measure the change in temperature of the accretion disk and determine pretty clearly what type of accretion this is, and ultimately that tells us how that black hole is feeding.
So actually here this afternoon.
Well, I'm only here for about another 2 or 3 hours.
Okay.
Yeah, and then I've got to catch a plane back to Australia. So.
Okay, so a little time to talk.
Yes. No, but we'll be a little bit done. Yeah.
Okay, so Rachel, here we have the newly reduced Hubble image. Okay, this one is 2026.
Yes, I can clearly see the 4 quasar images, so there must be a lensing galaxy here in the middle.
Yeah, this shows the amazing resolution of Hubble. You never get that separation from the ground.
No, it's quite spectacular, actually. Yeah.
Okay, so I'm going to move through the Hubble filters and drop from infrared into visible. Okay, and so if we keep an eye on the pair, okay, so similar brightness, but watch as we get down into the ultraviolet. You see the right hand one, and further into the ultraviolet.
Oh, that's a big challenge. That's a big challenge.
That's huge.
When we look at the greatest distance that our modern telescopes are able, we see bright quasars shining out. We can measure the mass of their black holes, and they are gigantic. Much, much larger than we would have expected would be possible. Is accretion enough to grow black holes so big? Well, without understanding accretion, we can't really answer that question.
It's a bit like a detective story. You know, you get little clues here and there, and the deductive reasoning is the physics. So physics allows you to do certain things and not to do other things. So it's really understanding what we're seeing and then allowing the physics to take us down another layer or two to stuff that we know is very natural and must happen.